Okay, so this is a review going over all of the different types of things that you might see when it comes to parametric equations on the BC exam, as well as what formulas you're going to need to know for this. I would say of all of the BC ideas, this one's probably the easiest because if you have the formulas memorized, there's not an awful lot of like trickery that they can use on the AP test to help you out, or to try and trick you, okay? So a couple of things that you just need to remember about parametric equations. The first thing is that all of the things that were true about particle motion in Calculus AB are also true about parametric equations. Excuse me. In reality, what you have to realize in these equations is that we really just have two particle motion problems in one. You'll usually be given some sort of function, sometimes a vector. Sometimes it'll give it to you like this, sometimes it'll give it to you like x prime of t and y prime of t. Either way, what you need to realize is that the x prime of t, or the dx dt, is the way they write it sometimes. That's just our velocity in the x like left and right, and then dy dt, or y prime of t, is just up and down. And they do function separate of each other unless you need it for a couple of different problems. Okay, so a lot of the same things are true. Okay, you're usually given a velocity function of some sort, and to find the acceleration, we still take the derivative of the velocity, and we take those separately. When we find the position, we are still going to use the integral of velocity, although it becomes more, it works very similarly depending on what you're asking. We still find the velocity by taking the derivative of position. So if you're given a position vector, which they do give you from time to time, to get to the velocity vector, we just take the derivative of each of the components separately. And the last one, the integral of speed, even though the definition of speed changes when we're talking about parametric equations, it is still the total distance traveled. Again, the only difference here is that many of these formulas are more complicated than they were before, but that doesn't mean the problems are any harder. It just means the formula is slightly more difficult. So let's take a look at each of these different things, what we do to find what we're looking for given a velocity vector. That is the assumption we're going to make in all of these, that we're actually using the velocity vector. So the first one that we're going to look at is if we're asked to find the acceleration vector, then all that's asking us to do is take the derivative of each of the two different dx dt and dy dt to get the components. Now, the only difference might be if we want the vector at a specific time, we just take those derivatives and then we plug that time in. And again, we do it separately. It's not just one number when we're looking for an acceleration vector. We leave the vector in that form. Okay, and again, that's pretty self-explanatory. The second one that we need to talk about is how to find the speed of the particle. Now, this derives from Pythagorean theorem, and we talked about that in class, but really the way that we find the speed given a velocity vector is we take the square root of our dx dt squared plus dy dt squared. And for the most part, it's really nice because they give us those different functions, those different velocity components in the problem for the most part. There's no absolute value on these because when you take the square root of something squared, it always comes out to be a positive number. If I want to know the position of a particle at a given time, again, we just realize that these are two separate particle motion problems that we just do separately, then we write our answer as that particular position. They'll give us an initial value like x or y, an initial x value and y value, and then we just do the integral from a to b of dx dt if you're looking for the x coordinate, or the integral from a to b, which both of those are times, of dy dt, which is just, that tells us the change in the y coordinate. And that tells us the position of the particle. Sometimes they just ask for the x coordinate, sometimes they just ask for the y coordinate, but in reality, that's all you do. You just have to do it twice instead of once. The definition to find the total distance traveled, so this is how we find total distance traveled, is by, it's the same formula as when we were doing particle motion. It's the integral from a to b of the speed. The difference here is our speed function is different. We have our dx dt and our dy dt squared adding together, and then we take the square root of it. That's the only difference. It's still the integral of the speed. We just use it slightly differently. And then if I want to know where a tangent line is horizontal or vertical, when we're talking about the slope of the tangent line, we find out where the tangent line is horizontal by setting dy dt equal to 0 And if I want to know where the tangent line might be vertical, I just take dx dt and I set that one equal to 0. And again, hopefully all of these kind of make sense. We've talked about these in class, so this shouldn't be something that we need to go over a ton, just kind of a good review, and hopefully you're kind of filling out the notes as we go through these. Now, these are not, okay, so if I want to find the slope of the tangent line, this is more a general question, but what we have to do is we remember that the slope is dy dt over dx dt. If I want to know the slope at a specific time, then I just put dy dt over dx dt, and then I plug that time in. Now again, this is different. I know in one dimension, when we're doing particle motion problems, this is just asking how fast the particle is going at a specific time. That's not what this is. This is actually the slope of a tangent line because parametric equations work differently. If I want to know where a particle is moving to the left or to the right at a specific time, we only deal with dx dt. dy dt has nothing to do with moving left or right. So what we do basically is we're asking at a specific time, is a particle moving to the left or right? We just take that time and we plug that into the derivative. If we're already given dx dt, you just plug it right in. If you're given a position function, you have to take the derivative. If you get a negative value, it's moving to the left. If you get a positive value, it's moving to the right. If we're asked where a particle is moving up or down, we do the exact same thing that we just talked about, but we use dy dt instead. Because dy dt tells us how we're moving in an upwards and downwards direction. If the value comes out to be negative, it's moving downward. If it comes out to be positive, then it's moving upward. Okay? The next one that we're asked from time to time is how to find out when the speed is a particular value. Now this is different from finding the speed at a particular time. This would be like, tell me at what time the speed is 4. What we would do to do that is we would just take our speed equation and we would set it equal to that number. That's the formula that we would set up. And then what we would do is we would just graph them and find out where they cross each other on the interval in question. Again, pretty easy, pretty self-explanatory. That one's not, as long as you understand what you're looking for, that one's not too bad. If I want to find where the slope is a particular value, like find the time when the slope of the tangent line is a particular value, what we do is we just take dy dt over dx dt and we set it equal to that particular number. So if I wanted to know at what time is the slope 1/2, I would just take dy dt and I'd graph that in y1, and I'd take dy dt over dx dt and graph that in y1. And then in y2, I would graph whatever number they want, and I would just find out where those two graphs cross on the interval in question. So again, most of this stuff when it comes to particle motion, or at least in my opinion, is very straightforward. This is all of the terms that you need to know. There are some examples that you can go over on the guided notes. Give them a shot. If you have any questions about any of this stuff, please let me know.